Guys, this is where we left off last time, and today we're going to be talking about the quantum mechanics model and the four quantum numbers, and also energy shells, if we have time. So these are two different depictions of the atom. We already know the nucleus, the proton, the neutron, the electron. This one you don't normally see. This one you see a lot. Like this is a conventional way of depicting the atom, but this way is completely wrong. Well, I can't say completely 100%, but it's like something like 80-70% wrong. This is more accurate. You get why maybe in the next video, but for now this one is inaccurate. I can't say it's 100% wrong, but it's inaccurate to the least. Okay, so now let's talk about the four quantum numbers. The first one is called the principal quantum number. It's represented by N, and it stands for energy level. So let me quickly hop to this slide over here. And as you can see, this is the Bohr model. So it's made by a guy named Bohr, and then this is only accurate. Again, this is also inaccurate, but this is accurate for the hydrogen atom. You'll see why later, probably in the next video. But for now, this is the nucleus, and then there are different shells for electrons. So we can assume like there are some electrons here and stuff. Cool electrons everywhere. Like this is the Bohr model, and for each shell, for each energy shell or energy level, for the first one there's one subshell. Second one there's two subshells. Third one there's three subshells. Just so you know, these are called energy levels, and these are levels that the electron float around the atom. So the electron goes like around the atom, and these are, well, the shell. These aren't the these aren't necessarily the path for the electron. For the hydrogen the hydrogen atom it is, but for other atoms this is not necessarily the path for the electrons. Like the electrons don't go around this path. Some of them goes like this, some of them goes, well, in other directions. It's like the electrons are, well, when I first learned about this I thought they were weird, but next time when we're talking about electron configuration, probably you'll understand why, well, these are. But the electrons don't flow this way, but there are different energy levels that these electrons are on. So basically, this is the first energy level, having one subshell. Second energy level, having two subshells. Third, having three. There technically an atom can have an infinite number of energy subshells. Energy shells. But after the seventh shell, we consider the electron to belong to another atom. So yeah, basically we only assume that the electron has like 7 energy shells. Okay, let's go back here, and that's basically the principal quantum number. It's called the energy level. Now is the angular quantum number, which is represented by L. It's the shape of the orbital of an electron. It might seem like a bit weird because, well, there are actually different shapes of, well, electrons. Basically there are 4 shapes. We call them like S, P, D, F. This does not have anything to do with like the PDF reader. It's just, well, for some reason humans decided to use these 4 letters. For as you can see here also, for the S subshell, it looks like a sphere. Yeah, it looks like a sphere. That's pretty much everything about it. And the hydrogen atom only has one of these s orbitals. That's why the Bohr model is accurate for this one, because the electrons can't go anywhere else. They have to flow along this orbital because it only has one. And hydrogen normally only has one electron. Normally, not the stable form of hydrogen, like the unstable element that can't be found in nature or something like that. So we're just assuming a stable hydrogen will have 2 electrons, but yeah. The p orbital looks a bit like this. it looks like a bow tie shape, the shape of a bow tie, or the infinity symbol, like this. One can be bigger than the other, but when we depict it, we generally, well, I just drew one that's larger than the other as well. But you get the idea. Generally, like we depict it this way. The d orbital is just basically, well, two p orbitals. The d orbital is not two p orbitals, but it looks as if it is two p orbitals. And there are many, many different shapes for F. Like, F is just complicated. So, anything more than, like, D, like this shape, it just gets complicated. And it gets, like, practically out of the picture. So there are many different shapes for F, and we need not bother ourselves with F for now. Okay. Now, again, let's hop to this slide over here. Like I said before, I drew something like this. This is a p orbital. Further questions about these orbitals will be answered probably in the next video when we talk about electron configuration. But for now, again, like I said, we can see this like an s orbital. And actually, let me do a quick sketch of the hydrogen atom. So this is one proton, and this is the electron orbital, and that is the electron. Basically, that's hydrogen. Well, elemental hydrogen anyway. Sorry, I don't mean elemental hydrogen. Like the hydrogen you see on the periodic table, the unstable form, like that. So it's got one shell only, and that shell is in the shape of an S. So yeah, the Bohr model works for hydrogen. Okay, now let's move on to the next number. It's got the magnetic quantum number, or m sub L. Not a 1, okay? L. Like, maybe I should do a bit of that thing, but like, it's like m sub L. That stands for orientation. The word orientation means like ways or aspects to look at something. So when we actually think about it, how many ways are there for an s orbital, which is just a sphere? You gotta think like 3D now. Like just a sphere to be put around a nucleus. There can only be one way to like put it, right? Basically there is only one way. But for an orbital like, for example, say P, this is the nucleus. A p orbital can be put this way, or it can be put this way. We call it orientations because if you, whoa, oops, I accidentally pressed something that I should have pressed. Oops. Anyways, we're back. So, okay. Like I said, a p orbital can be placed this way or this way. Basically, these are just different ways of looking at the p orbital. The p orbital, it has like 3 different orientations. If we think about it like 3D, in a 3D manner, it can also be placed like this one's sticking out, that one like behind. I don't know how to draw 3D, but that one's behind. This one's like sticking out. So these are just different ways to look at it. But when it's like in subshells, these forms are put around the atom, like different forms put around the atom. Sometimes an atom will like, for example, only have 2 orientations. Then, in this case, for like a p orbital, ignore the third. But now, so this is basically orientations. And by the way, if we like combine these and put them on one atom, 2 s orbitals does not equal 1 d orbital. Okay, now the fourth one, we don't use that quite often because in 6th grade chemistry, like later we use it a lot, but in 6th grade chemistry, like the spin direction isn't used a lot. So it can be clockwise or counterclockwise. It's just the way the electron spins. So again, assume this is an s orbital. The electron's here. It spins this way. Assume, okay? I don't know which way it spins, but assume it spins this way, clockwise. Now this one spins counterclockwise. Well, basically that's everything to these 4 numbers. Now let's talk about valence electrons. So valence electrons are the outermost electrons, and according to a rule called the octet rule, an atom must have 8 electrons to be stable. This this does not apply to every single atom, but it applies to most of them. Only two atoms need two electrons to be stable. And if you think about it, it's like, well, basically intuitive, because how can a hydrogen atom have so many electrons? One proton, one positive charge, and like, wait, 1, 2, 3, 4, 5, 6, 7, 8. 8 negative charge, 7 negative. That was a lot of negative charge. Like, this is just my way of remembering that. But anyways, a hydrogen atom only needs 2 electrons to be stable. Only 2. Yeah. I mean, yeah, 2 electrons, but basically what I should be saying is 2 valence electrons, which is the electrons on the outermost shell. I don't know if I explained this clearly or if you understand, but on the outermost shell, which is like, whoops, in this case, gonna be this shell over here. It has to have like 8 electrons on this shell. It doesn't matter how much electrons you have like below, or like you can have 8, or you can like abandon the outer shell completely, and then like inner shells will have electrons. Yeah. So this is called the octet rule. So this is just a rule for elements to be stable. Okay. Each like orbital in each orientation can only have a maximum of 2 electrons in it. This is another reason of why the hydrogen atom, which only has one s orbital, only needs 2 electrons to be stable. Because it can only contain 2 electrons. Like, it can't contain any more. So it has to be 2 electrons to make it stable. Makes sense. However, when we go to like p orbitals, there are 3 orientations, like I demonstrated before. So each orientation can hold 2 electrons. So 3 orientations, which is 3 ways to put this t orbital over an atom. So you can imagine putting 3 t orbitals. Well, why did I say t? I meant p. Putting 3 p orbitals. Each orbital can contain a maximum of 2 electrons. So 2 times 3 equals 6. Which is, well, 1 p orbital. It can have a maximum of 6 electrons. And a d orbital has 5 orientations, giving you 10 electrons in total. F orbitals, 7 orientation, 14 total electrons. So when we're doing electron configuration, this can be really useful. You will see why tomorrow, or should I say in the next video. Anyways, let's go here. So like I said, the s orbital can also be, well, said as like L equals 0, P L equals 1, D L equals 2, and F L equals 3. So it starts from 0. So these are pretty much everything about the 4 quantum numbers and energy shells that you need to know for 6th grade. Tomorrow we will be talking about electron configuration, and we'll be extending on these energy shells and stuff. So now is when it starts to get hard, but simultaneously fun. For me, this is where chemistry starts to get really, really fun. Tomorrow, you will feel a whole lot more powerful because, well, you know a whole lot more stuff. After that, we're going to be talking about chemical reactions, which is going to be even more fun. But anyways, that's all for today, and goodbye, I guess.